we were talking last time about inheritance, and we were looking at pure virtual functions, and that's kind of what we looked at yesterday, looking at this num class. Okay, so if I asked you on a test, I said, multiple choice question, perhaps. Num is a what kind of class?
Abstract.
Say it. Somebody say it. Abstract class. And Ronaldo, what does it mean when a class is abstract? Cannot be instantiated. And the reason is quite simple. Cannot be instantiated because one of its method, at least one method, but must be at least one method, is pure virtual. So therefore it's an abstract class. We don't have an abstract keyword in C++, like some other languages. But it's abstract. And now, these classes actually are subclasses, and what they do is they take this pure virtual method display, which has no parameters void, and they code it. And by code, this is just a comment, and they code it here, and they code it here, so therefore they override that, and they become concrete classes, so we can instantiate objects from those classes. That's what we looked at last time. Okay, so we can continue that. Now, let's take a look at this class here. So notice what I did a little trick here. I said pound define VT virtual. See how tricky that is? Because if you look at this code, say, what is VT? We didn't learn that. Yeah, because it doesn't exist. So I just base it up in a little trick using the preprocessor by saying pound define VT virtual. So every time the preprocessor sees VT, it says virtual. It doesn't matter where it is. It could be inside a comment. It could be inside anywhere. It'll just change it. Okay? The preprocessor is not the smartest processing system at all. Okay, so what I'm doing is I'm creating a bunch of virtual methods. Deposit, withdraw, double, and display. Notice display is no longer pure virtual, but it's still what? Still virtual. So I'm basically tagging all these methods. Deposit, withdraw, balance, display, even the destructor as virtual methods. So now then I have some other properties like enum, sslen equal 12, so sslen is a 12, unsigned account number, char, array, ss, and then private. Why did I make some properties protected and some properties private? Why would I do that? Why would I want to make some properties protected?
Inheritance.
Because I'm planning for inheritance. Because if I have a subclass of account, it will view protected like what? Like public.
Yeah.
But clients of account will view protected as
Private.
private. Okay, that's why. So when you see protected, if you're not planning for inheritance, then don't do it, because there's no sense in doing it. So when you have protected properties, protected methods, protected properties, those are usually because you're planning for inheritance. Okay, this is the implementation. So notice that I have a lot of virtual functions. Now, the compiler sees the virtual keyword, because that's basically the translation of VT. So once I go to the CPP implementation, notice that my balance, deposit, withdraw, display, I no longer have to say virtual, because once they're declared as virtual in the header, they're virtual. So you can put virtual here, but it doesn't make any difference. If it wasn't in the header, it's not virtual, that'll be an error. If you put virtual, it says, okay, I already know that. So, why would we make methods virtual and not pure virtual? Because in the other class, in num, we had display as a pure virtual method, which means that num was abstract. But in this case, all of the methods are virtual, but none of them are pure virtual, which means that the account class is not abstract, it's what? C-O-N-C? Concrete. Concrete, right? You guys know what concrete means, that you can instantiate it. It's a real class you can instantiate. So why would I make them virtual?
Make use of the same functions.
I cannot hear what you're saying.
Make use of the same functions in the derived classes.
Okay. Again, the answer is almost the same as Ronaldo gave us, because I'm planning for inheritance, and I'm going to do what with these methods? I'm going to override them in sub-account classes. That way, if I have a pointer to a sub-account class, and it's got an override on display, it'll run that display.
But Professor,
Yeah.
what will we get in pure virtual? If we take pure virtual, then we use only read only, right? We cannot write it. Like we cannot overwrite it.
If it's pure virtual, well, any method, whether it's virtual, non-virtual, pure virtual, any method in a superclass comes down here. So if I have a pure virtual method in the superclass, and I subclass this, I inherit that pure virtual method. So if I don't override that method, I'm also abstract. So any class that subclasses an abstract class and doesn't override the pure virtual methods in the superclass stays abstract. So you have to override it if you want to actually create objects of this class. Why do we have abstract classes? If I gave you like a short answer question, what's the purpose of abstract classes? That's a good answer. I wouldn't think of saying it that way, but I understand what you're saying. He's saying like a template. So I wouldn't say it exactly the same way, but I know where you're coming from. Basically what you want to do is you have a class, then you have a different class, and you realize, hey, these guys are different from each other, but there's a lot of sameness. There's a lot of things that are the same. So what you do, you take that sameness, you factor it into that superclass. And then you inherit it into both of them, and you specialize these guys by adding so-called appendant members. So here you have the base class. The base class has the common stuff. It's nice because if you change the common stuff, you've changed it in all of them. So it's consistency, right? And if you develop and test the common stuff up here, then it's really easy to just specialize your class because you know everything else that you inherited already is going to work. Okay, true or false? Abstract classes cannot define method codes. True or false? False. They can define method codes. They just can't define the pure virtual. The other methods can be defined. So therefore, if you subclass an abstract class, the methods that are defined, if you don't want to or don't have to override them, don't override them. If you're not going to override a particular abstract class method, then don't make that method what? Virtual.
Yeah.
Don't make it virtual. Because you just want to use that method. That method is fixed. For example, let's say I want to create a class, and this class is going to have a static member called count. And it's going to have a static method called getCount. So make it static. Count, getCount. So I don't care what type this is. If you have a subclass, you have a subclass, you have a subclass. If you create objects, each of them will call count plus plus, count plus plus, count plus plus. So it's going to increment. So just inherit that method. It's not virtual. You don't need to do anything with that. So you have flexibility.
So Professor, what is the use of virtual then?
The virtual is usually implemented only in cases where you want a subclass to override the method. And you are dealing with pointers, typically, or references to objects, which could be coming here, or here, or here, or here. Now, let me just make one thing perfectly clear to everyone. We talked about, usually when we talk about inheritance, we use that funny word ISA, right? We talked about the ISA word. So if a class, so if you have a code, I know this is a terrible room for, I don't know why they don't have any boards in this room. It's really very, they have a very nice screen, but no boards. Let's see, where is this? Oh, this is the manual screen. I'm looking for a button. See, next door you can... am I getting older or just the stupidity of my brain? I don't know. All right, so now I forgot what I was going to do.
ISA?
Oh, yeah, thank you. Okay, so if you have so let's say you have a class A, right? So you have a class A, looks something like this. Then you have a class B, something like this. Then you have a class, let's say C. And let's just add one class. So maybe I can add a D. Notice that arrows go up, right? So, base class, two subclasses, and here's a subclass of a subclass, right? So, if you think of it, if you think of ISA, and ISA, because these are public inheritances. Remember, public means that you are exposing the interface of A is exposed to the clients of the interface of C and A. So if you have a public inheritance from, if C is a subclass of A, then clients of C see the public interface of C, but they also see the public interface of A. So therefore, if you can call methods in A, then you are an A. Because you have all the methods, so you are an A. Okay, so that's why we have the ISA. Now, in C++, we create pointers. So for example, let's say we have A star, B star, C star, and D star. So these stars are basically pointers to the respective classes, and I can create actual variables here, A, B, C, and D. Okay, so what is D? Is it an object?
Yeah. Yes.
No. Where's the object? It's a pointer, isn't it? If I say int star P, is P an integer? So it's just a pointer. Okay, so it's an int pointer, so these are A, B, C, D pointers, right? These are just pointers. There are no objects here. Okay. Now, we can create objects. So therefore, we can, let's say we have an object, something we say new C. Okay, what's that going to do? That's going to create one of these things. All right? So, and so I'm going to say C is equal to new C. Does that make sense? Does that make sense?
Yes.
It makes sense. Okay. Just make sure. Chris?
Isn't C a C pointer?
Oh. No, C pointer. No. This is a big C. This is the little c. Little c. Little d. Little b. Okay? Does that make sense now? Yes?
Yeah.
Okay. What type is this? C pointer. What type does this call return? A pointer to a C object. So it looks like a match because, so this returns a type of C star. And this is a C star, right? Now, can I say A is equal to C? These are now pointers. Can the pointer A equal to C?
Yeah.
Well, if A is equal to C, then what's happening is that A is pointing at a C object. I'll make the objects look like this. So this is a C object, and I'm pointing it to C. So this is a C object. Okay? And now I'm saying A is equal to C, which means I'm assigning the address value here into the address of a value of A, which is address of the C object. COBJ, C object. You think it's okay or no? How many people think it's okay? Okay, so why is it okay?
Because there is a relationship with that.
Well, A can only point to things that are of type A. So is the C object of type A? You can see C is an A. It has everything that A is supposed to have, so it's fine. Now, suppose there's a method here called M1, and suppose there's a method here called M4. Which methods can I call here? C pointer M1. Can I call C pointer M4? Sure, why not, right? Because I have these methods. I inherited M1, that's my inherited method, this is my appendant method. So both of these are on C, so C pointer can invoke M1 or M4. Again, as long as it's public and this is not private, right? Okay. Now, A is pointing at the same object. Which methods can A pointer invoke? Which methods can A pointer invoke?
M1.
Uh,
M1.
M1. What about M4? But doesn't this thing have access to M4? Sure it does. So actually, you're right. A pointer, even though it's pointing at a C object, cannot invoke appendant C methods. Any idea why? Any idea why?
It is not inheriting.
Louder.
Because it is not inheriting method.
No. We know why it can't. But it should, because A is pointing at a C, right? Why not?
Compiler reads from top to bottom and then
Go ahead.
it will read from top to bottom, so it will read case class first, then come to the derived class.
In M4 method, before pointing to
Okay. Before you answer the question, okay, I made everybody think. That was the goal, to make them think. Now, what is this? Okay, so someplace I said new A, right? So in a different part of the program, is it possible for me to say A pointer M1 on this object? Yeah. Yeah, of course. Is it possible for me to say A pointer M4? No, why not? This object doesn't have it, right? This is a correct connection, but this object doesn't have M4. This is a correct connection, and this object has M4. And yet you're telling me I can't call M4.
Because it is not.
And you're right.
Because it is
But
not-
I want you to tell me why it's right. Now you can look at these two and say, why is this okay? Why is this not okay? Why is A pointer M1 okay? And A pointer M1 okay, but A pointer M3 is not okay.
M4 is not in the scope of
Size of A is not equal to size of
Louder?
size of A is not equal to size of C.
Oh, it might be. We don't know that. They might be the same size. Two classes can be the same size even though they're different.
But there's an appendant method in C bar,
That's true.
so it's going to be
But size of returns the size of the data.
in bytes.
So, anybody else?
And M4 is not inside the scope of.
Okay, it's a much simpler explanation, and it always is, right? It's a much simpler explanation. You understand that A here and A here are the same A. You understand that, right? They're the same A. So, what if we had a condition, if some condition is true, do this, else do that. So now, when I'm coming out of this conditional, do I know, until the condition is evaluated, whether A will be pointing at an A object or a C object? Do I know? The answer is no, I don't. Does the compiler know what's going to happen at runtime? No. So therefore, the compiler does not pass this because it says, I can only allow an A pointer to invoke A methods. Only. Only. Because I have no reason to know that sometimes it's going to be okay, like here, but if this is the case, it's not okay. Because if the condition is true, A is pointing at an A object, then this invocation is a runtime exception. But if this condition is false, then A points to C object, then this is perfectly fine. Well, it can't be both ways. The compiler is just going to say you can only, so the compiler, you can only invoke the methods here. If you wanted to invoke the method M3 from this, how would you do it? Anybody have an idea?
Scope. Put it in the same scope.
No.
Reinterpret cast.
Okay, so we would have to cast our pointer A as a C pointer. If we cast it as a C pointer, that cast will succeed. In this case, it will fail, in this case, at runtime. So we'd have to be able to check it. Does anybody know of an operator that checks types in C++? Look it up. Type ID, Typeid. Type ID. Type ID is one way of checking something. So type ID, so basically, if you did a type ID of A, does it equal to A? Yes. Type ID, does it equal to A? Yes. Type ID, does it equal to C? Yes. Type ID, does it equal to C? No. So A, type ID of A, it will be either an A pointer, or a C pointer, or an A pointer and a C pointer, because this has both. So if you want to check if this is an A pointer, yes it is. Is it a C pointer? Yes it is. Is it an A pointer? Yes it is. Is it a C pointer? No, it's not. Now we have another class, D. So A could also be pointing at a D object, right? And D has defined another method. Method 7. Method 7. So again, I could have if this, else this, if else that, blah, blah, blah. It's possible that I can have this. Is this a legal statement? Sure, because A is pointing at a D, which is a C, which is an A. So this can invoke all the methods in the D object that have been inherited from A. How about the ones in B? No? No? Not unless you? What does this mean? Hugs? Hugging? Not unless you cast. Look up type ID. Okay, you get the idea. So, all right. So that's the implementation. Now, we talked about this free checking class, so basically this is a public virtual. Now this is very interesting. Class free checking, public virtual account. This is a whole new virtual. This has nothing to do with the virtual methods. This is saying that the inheritance is virtual. And so what does it mean to class free checking that it's a public subclass? We know what that means. What does it mean to free checking that it's a public virtual subclass? Let me give you a clue. As far as free checking is concerned, this means nothing. Nothing. Okay? Got it? Means nothing. So, therefore, free checking is just a public subclass. Virtual does not mean anything to free checking, but it will mean something to subclasses of free checking. Okay. So, you can see that it's going to be a virtual account. Now, what I'm doing is, so I have free checking as a subclass, then I'm going to create another class. Joint account, which I'm saying is also a virtual subclass. Okay. So notice that I have another constructor, default constructor. I have my override of the virtual. I don't know if it's virtual or pure virtual. I add another appended member. This is the joint social security number. So what I have here is I have account here. I have free checking account, and then I have joint checking account. Both of them are subclasses of account. But they're both virtual subclasses. And the reason we're doing that is because we're doing something that a lot of languages don't allow us to do at all. And that is to create a subclass, which is going to be a subclass of both this one and this one, which is allowed and is referred to as diamond inheritance. Sounds very, very fancy. Sounds like you're going to make a lot of money, but there's no money involved. So you have a class, you have two subclasses, and then you have a subclass which extends both the subclasses. Therefore, it extends the superclass 2 times. And believe it or not, in C++, if you don't make these classes virtual, if you don't make the inheritance virtual to these 2 subclasses, then this diamond on the bottom is going to get 2 copies of the properties of the top class, which you can access independently. Sounds kind of crazy. But if you make it virtual, it says that whenever you subclass 2 classes that are virtually subclassed A, blend that A into a single A. Okay? That's what it means. I'm not going to make a big deal out of it, just let you know about it. Okay, so let's not dwell too much on it. You can look at some of the code. Okay, I want to talk about templates, because we were starting to talk about templates last time. Templates basically is a way to create generic code without pointers, without void pointers, because the only way we create generic code is with void pointers. So template functions are generic functions. They allow processing any type of element. What is a generic function? A generic function is a function that takes not only different values for parameters, but takes different parameter types. So you can have a function that takes an int. You can get different ints. That's just a regular function. But what if you had a function f, and it could take any type? It could take a int, it could take a f stream, it could take a rational, it could take a fraction, it could take a string, anything. In fact, you create a new one, it can take that too. So we're creating functions that the type of parameters can change upon what you want to make it. So the implementation is different. The generic void may be a little bit easier. And so what we're going to do is we're going to look at something like this. So let's take a look at this. So this, the keyword here is template. In the brackets we have class T. Okay, so template is the keyword. Template class T, void, swap, and then what it looks like is the swap method takes 2 parameters by reference, A and B, both of type T. But there's no such type T. You know, it says class T. It says, so the template is for class T, which means that you can have class T be anything you want it to be. So if you want it to be an int, it could be a swap of int reference, int reference. If you say if you say T is going to be a string, you're going to swap string reference, string reference. Okay, so if we allow, if you want to make it easier for yourself, if you haven't seen this before, imagine that T is an int. Just replace it with int, int, int. So if it's an int, basically int temp is A gets B, and B gets temp. Easy. It's a swap. But if you allow T to be something else, if it's a string, then we have 2 string references. String temp is A is B is temp, swaps 2 strings. If they're rationals, same thing. Class T is rational. So the question is, where do we specify what type T is going to be in this case? And by the way, T is not a special letter. You can say class U. If you say class U, then you have U, U, and U. If you want to call it class UB, lowercase, fine. Uppercase, fine. Any identifier name can be. But most people use T for a single type. And if you have 2 types, as you see soon, then you can have T and S or T and R, whatever you want them. Keep it simple. Unless you want to keep it less simple but more clear. All right, so if you look over here at the code is basically running. And if you look at this code, it has a couple of ints, a couple of doubles, a couple of string pointers. It does a cout of a lot of these different things. And then it calls swap, swap, swap. But swap is this method right here, or this function. I call it, not going to call it a method because it's not inside of a class, so therefore it's just a function. Called swap. But swap is not really a function, it's a template. There's your template word, Chris, right? Template. It's basically, this is what functions that swap do. They take two elements of the same type, perhaps, and they assign one of them to a temporary, the B to A, and A gets a temporary, and they succeed. So when the compiler, the first part before the compiler can compile this code, we have to generate functions. So there's another component to C++ called the template generator. The template generator basically, as we scan over this, we see the template generator makes a note that this is a template for a function called swap. When you see a call to swap, it says, hey, I know that function. Now let me see what these parameters are, because T and T, well, in this case, notice that I and J are both ints, So therefore, the template generator creates a class called void swap int ampersand a comma int ampersand b bracket int temp a equals b equals done. But then the template generator sees, oh, it's another call to swap, but this time D and E are type doubles. So therefore, guess what? It creates another version of swap replacing T with double. And then it sees another call to swap, and this time S1 and S2 are char pointers. So therefore, it's going to create a third version where this is going to be char pointer ampersand A, char pointer ampersand B. So we're going to take two char pointers by reference. Okay, are you with me? Okay, and so basically what happens, they all succeed. So when after I swap them and I print them out, I get them in different orders. So here's the output. You can see 3 and 5 swapped. These two swapped. These two swapped. So it's a very, very simple idea, right? So templates, very, very simple idea. Yes?
How much space does that generic function reserve for that?
So the source code has to have the template, and then that's the source code, but then the template generator actually adds to the source code by generating, in this case, 3 copies of this function. So if you have a very, very long generic function with a template, it's going to create 3 times the code. If you have 3 different calls. If you have 25 different calls, 25 times the function. So it can blow your code up.
No, Professor. I'm asking you like, if you put normal int over there, so it will result 32-bit or depending upon our parameter, right?
Yes?
So for generic type, how much space it will reserve?
Well, I'm not sure what your question is.
In function, if I define int, right?
Here?
So it will
Here?
reserve, yeah.
Or here?
No, over the template.
If I
Instead
say,
of template,
if I put int,
yeah, so it will reserve some space, right, for int to carry out that function. So for generic function,
for passing the parameters and
Yeah,
returning,
yeah.
well, all that space is reserved on the stack. Parameter passing to functions and return values are done through the stack. So when a function returns, it actually puts its return value on the stack, and when the top frame goes back to the bottom frame removes that from the stack before that frame is removed.
But for generic function, how much space it reserved? Like 32-bit, 64-bit, or it depends?
Hold on a second. So you have to understand that this is a template.
Okay.
This is not compiled. So the template generator sees this, remembers the definition of the template, and then it generates 3 codes. This code will return 4 bytes, this one 8 bytes, and this one probably 4 bytes again, because there are 3 different functions. So once we see the calls to them, then we see how many different versions of the template have to be generated. Okay? All right. Here's another example. So here's an example of a template. This is called binary search. Binary search, we're going to look for an array of elements. What type? Some type. And the key is that type. And how big is this array? It's n. Okay, so what I'm going to do is I say template class K. Why K? Because it's a good letter. I can say class T, then every K is a T. But whatever you want, any identifier is fine. So all I'm saying here is, so now whenever I have a binary bin search call, I look at the type of the key, the type of the array. They have to be the same types. This has to be an array of these, and this has to be a key of the same type. Does that make sense? So if you have, for example, an int, an array of double pointers, that's not going to work, because then they're not the same K. That means you want 2 different kinds. If you want 2 different kinds, then you can say template class K, class J. You can create 2 of them, and then it says 2 different parameters, 2 different types. Fine. I'll generate a template that has one type is this, one type is that. But if you have only a single type, then these have to match in type. Okay, so this is called a binary search. Notice that I'm looking at comparisons like if key is greater than a sub mid. A is an array of something. So a sub mid is a mid element greater than. Now, if k is a rational, this will fail if the rational doesn't have the method greater than overloaded, that operator. Does that make sense? So the generator, if you put class k as rational, will generate it for rationals. But the compiler may still give you a compiler error. Why? Because the rational class doesn't have that operator defined. So just because it can be generated as a template doesn't mean that it's going to compile. So before the compiler sees it, the template generator generates it, and then the compiler tries to compare. Now here's an idea of another slightly different, searching a generic array for a particular compatible element. So in this case I have a template. Notice that I have two classes, so I'm going to call one K, one L. Okay, I'm going to return a pointer to K, and K is an array of elements. So A is an array of elements, but the key is of type L. So I'm sending a key of this type and an array of that type. So next thing I'm going to do is I'm also going to send, this is going to be a compare function. So now I'm getting very, very fancy here. I'm sending CMP is a pointer to a function that returns an int and takes an L and a K. You follow what I'm saying? So we're going to be able to compare an L and a K. An L is just the key, and a K is going to be an A sub I. It's going to be a particular value. Okay, he's going to show you that. I'm not going to bother too much with it. You can take a look at it some more. Okay, skip that. Skip that. Skip that. All right, now this gets more intense. So I'm going to try to be as nice as I can be. Okay, so here we have a class, which is a template class. So template class T, class list iterator. Nothing is, it just looks very scary if you haven't seen this before, but it's not. Because basically what you're saying is, I have a class called class list iterator, and I have a generic type T in it. Okay? So that's what. So this is the template. It's simply going to have list iterator. So the next thing I'm going to have is I'm going to have a template. So this is just a declaration for this. Type T must define operator equal equal and overload this too. But you're going to see that in a second. And so this class right there is going to be a generic class. Generic class of class T. So notice it says I am a friend of class list iterator T. So if somebody creates a new object of class, let's say int, then T becomes int, and you become a friend of class list iterator int. So that T is filled in. So whatever T becomes, every T becomes that type. So if this is a double, that's a double. List head null. Okay, when you create a default, easy. List T ampersand C, colon head new cell. Notice that cell is another template. So we have a cell, a list iterator, and a list. The list is going to have a list of cells. So this is going to be a cell. We're going to need a cell inside the list. And the list iterator is going to be a class that's going to be able to go through those. Now, this looks fairly complicated. I understand that. But basically the idea is, if you look at this method here, and let's say our T value is equal to an int, always substitute int for simplicity. If you want to append something, you're going to append an int reference C, and then you're going to return insert C into the last position. So every T just gets converted to a particular type. Now the reason this looks a little more complicated is because we have a list using a cell, and then we have a list iterator iterating through a list. So I'm not going to bother too much with that, but you can sort of see the way it's done. So this is template class T, class list iterator, and notice it has list iterator, list T ampersand X. So here is the type in the constructor. This is the parameter. So the list iterator gets into its constructor. It gets a list of type T, the same type as it's parameterized. So list iterator iterates list of, let's say, list of doubles. So therefore the list iterator gets into its constructor a double list reference called X, and it puts the X into L. What's L? It's a list double reference. So it references that one. So there's a lot of code. Now the nice thing about it is that it's very, very powerful. The even better thing about it is that if you don't like to use templates, but you like to use templates, but you don't like to write them, there is something called STL, and STL are standard template library. So here you can see the most basic template class cell. Cell basically is very, very simple. It's a cell which is going to, what it's going to be, it's going to be a cell, it's going to be like a node, right? It's going to have a value, it's going to have some pointers. So you can see that the cell has a type T. So we have, as far as the properties are concerned, val is a pointer to t, val is a pointer to t, and then next is a pointer to a cell of type t. So a cell can point to itself. This is a cell parameterized for t, cell templated for t, therefore next is a pointer to a cell templated for t. So it allows you to link the cells together. Okay? All right, so I'm not going to do too much there. Okay, that's all I'm going to do. I just wanted you to see that. But now what I'm going to do is I'm going to show you, this is going to be a little bit easier. These are going to be pre-made templates. So pre-made templates are templates that are already part of the C++ language. And that part is called STL. So I figured if I showed you STL first, you'd think it's hard. But I figured that if I do this one first, you won't think it's hard anymore, right? See, you see how I work? Like, well, that was hard. Okay, so I need you to be able to, if I put a very simple class, I'm not going to nest classes for a test. I might create a templated class and some code. You should be able to see how the code is going to instantiate the class. But I'm not going to nest the classes. Like, we're not going to have a cell and a list iterator and a linked list. We're not going to do that. Very simple one. Just want to see how it works. So know how the template keyword works. Okay, so let's look at STL, if we can. Okay. Okay, so STL, Standard Template Library. Standard means you don't have to do anything. Just use it. Okay, so basically STL is divided into, I don't know why I say 3 basic components, but I guess I'm going to say 4 basic components. Well, maybe 3 basic components. Containers, iterators, algorithms are the basic components, and then functors are the 4th component, which is not so basic. But it's kind of fun. And when you see how functors work, you're going to say, oh, that's how they did it. All right. All right, so containers are collections of objects such as vectors, decks, lists, queues, stacks, blah, blah, blah. They can be associative containers, collections such as set, map, or multi-set. Associative containers are containers that basically have a key-value pair. Or adapters, and adapters are also stacks queue, priority queue, etc., etc. Let's take a look how to use these things. It's easier to see how you use them versus defining everything. So I'm going to create, so basically vector, if you're going to use a vector, STL, container, you have to pound include vector in brackets. Okay? Now, what kind of vector am I making? I'm making an int vector. So vector int, I can put whatever I want into here. If I say vector rational, fine. Vector type, my vector 20. So I'm creating a vector of 20 elements, each of which is of type int. So since I have a vector, vector allows me to use bracket notation. So vector sub 8 is equal to 13. So I'm putting that element into the vector. Vector string, my string vector 15. V3 is equal to hello. Okay? All right. Associative containers like set. We know what sets are. Sets are non-duplicate, unordered elements. Maps are collections of key-value pairs. Multi-set and multi-map allows you duplicate keys. So multi-set is like a set with multiple elements being allowed to be in there twice, 2 to 3 times. Multi-map is a map of key values where the same key can be in more than once. And then we have something very cool called bit set. There are a series of bits, like a vector of Boolean values. And they implement operations like bitwise AND, bitwise OR, bitwise XOR. Okay, so let's take a look at iterators. So iterators, here we go. So vector int, my int vector 20, for int I equals 0 to 19, vi is equal to 2 times I. Does everybody understand what this code is doing? Yes? Okay, so I'm creating a vector of size 20, and I'm initializing all the values. What's the value of v19? 38, okay, good. All right, so now, look very closely what I'm going to do. VI is an object. The type of the object is vector int colon iterator. Okay, does anybody have any idea what the heck that is? First of all, I want VI to have a relationship with vector int, so that part is okay. But it's not a vector int, it's a vector int iterator. Anybody have an idea what that is? Notice that we have a scope resolution operator between the vector int and the iterator. The iterator is a nested class inside the vector. It's a nested class defined inside of vector. So therefore, when you have vector int colon iterator, because the iterator is nested inside of the vector class t, your iterator is also going to be iterating through values of type int. Because it's nested inside class t vector, the iterator will also be parameterized for type t. So the parameter types are going to be t. So, here's the code. So what does the iterator do? Allows you to look at the elements regardless of how they stored it. They're stored in linked lists with pointers. You don't have to care about pointers. If they're stored in an array, you don't have to care about the indexes. You just get an iterator that says, okay, let's go. From beginning to end, let's go. You get them any way you want to, and then I'll print them out. The first thing we're going to do is we're going to say VI is equal to V begin. So begin is a method in which class? It's no. What type is V? Oh, hold on a second. That's supposed to be V. Something went wrong here. Okay, so that's supposed to be a vector int v20, and then here we have v, right? So what type is v? Vector int. Like, it's better to say vector int than vector, because vector int tells me that you know the type. Okay, so it's a vector int. So v.begin goes into vi, and then we have a code that looks like this: while vi not equal to v.end. Okay, so do you have any idea what's going on here? Vi equal to v begin. There's some value going into vi that's marking the beginning of the vector. And while this value that's marking the beginning of the vector is not equal to the value that's marking the end of the vector, cout star vi. Well, if I say star vi, it sort of tells you about something about vi. What is vi? What type is vi? Huh? Int pointer. Oh, okay. So it's an int pointer. How do I know it's an int pointer? Because vi is iterating through a vector of ints. So therefore, when you say star vi, it dereferences. So that means that vi was pointing at the first element of the collection. It's pointing to it. It has its address. So when I dereference it, it prints out the first value. What value is that? 0. And then I say vi plus plus. Then I say vi plus plus. So what does that do? It moves vi to the next element. How? I don't care. I don't care if it's indexing it, if it's following pointers. Plus plus is going to make the vi point to the next element. So once it's moved to the next element, if it's not the end, print it, keep moving. Eventually, it looks like vi plus plus is going to move it on to the end value, and then this condition will be false. It will be equal to the end, in which case we'll drop out and we'll print an end line. So we process a container using an iterator. Okay, here's an example of algorithms that are part of STL. So in this case, I'm going to say vector int my vector 20. I don't know why I'm doing my vector in v.
Yeah.
Just v. All right, so then I say generate. Generate is an algorithm. What's an algorithm? It's an STL. You can use it if you say pound include algorithm. Pound include vector. Okay? So generate. What's v begin? It marks the beginning of the vector. What's vn? Marks the end of the vector. Okay. Do we know what type the vector is? The vector is a vector int. Therefore, the compiler knows that this is a vector int. Therefore, this is going in as an int pointer. So the pointer is an int pointer. If this was a vector string or a vector double or a vector long double, then the pointer would be a different pointer, but you don't care about it. You don't have to know about it. So basically, what you're getting is you're getting the address of the first element, and here you're getting the address of the end of the last element, which means the beginning of the no element. You're at the end of the buffer. And rand, what's rand? What's rand? Rand what?
It's a function.
It's a functional pointer. You've used rand before, right?
Yeah.
Of course. So therefore this is a function. So this is a function that returns what? Returns an int. Well, that makes sense. So basically what the thing is going to do, it's going to take this pointer, assign it to a function, loop for this one, as this is iterating through here, and calling this function and assigning a value into all the elements in the vector. So the vector gets a random initialization. All right. Let's take a look at another interesting part of C++, something called a functor. Almost sounds like it's wrong. Functor. Don't you mean function? What's wrong with this functor? All right. It's a functor. So STL includes classes that overload the function call operator parentheses. It's a very weird thing. Because if you have an object, call it X, and X is an object of class C, and C overloads this operator, then you're going to call this, now this is an operator, overloaded operator. So when you call this operator on the object, it looks like a function call. Okay, you're going to say A, semicolon. So people looking at the code say, he's calling a function called A. No, I'm not. I'm invoking an overloaded operator on the object A. Furthermore, I can take parameters into the overloaded operator, which means that I can overload the operator parentheses and take parameters into it. If I take an int, it will look like this: A, parentheses, 6, parentheses. Now it really looks like a function. I'm passing a 6 into it. So what is a functor? A functor is an object that looks like a function. So a functor is kind of a function, but because it's connected to an object, and an object has properties, a functor is a function that has a state, has values, has properties. You can put 16 properties into the functor. So when you call a function, the function has got values in it, and could have other methods in it too. Okay, that looks very confusing. All right, so let's see how that would work. Now, I'm going to show you how to create your own functors. It's a very complicated one. It's a very complicated one. Hopefully. And I have very long names here. Remember how I use V for vector? I don't use that anymore. I use very, very long names here. Oh gosh, okay. So let's take a look. So we are going to have, what's the name? First of all, find the name of the method. Okay, you found it. Okay. So notice what we have. We have template, class, input operator, class, output operator, class, unary operator. So all we did was basically we're creating a function template, right? Function template. So we have 3 different types. So what is this? That's the return type. What type is that? I don't know. It's this type, right? So this is going to get called. This is the name of the function. It takes an input operator, it's one of these things. It takes another input operator, it's one of these things again. It takes an output operator, and then it has a unary operator called OP. Okay? Now, so what you're having here is first and last, and first and last. I guess we can sort of surmise that this is the input iterator, and this is the input iterator, that somehow this is doing what? This is referring to the first element and it's referring to the last element, right? Okay, so as long as they're not equal to each other, what does that mean? As long as they're not equal to each other, that means there are elements. Because if they're equal to each other, we know that from our pointers. If the first pointer is pointing at the end of the end, that means there's no more data in the container or in the object. So while first is not equal to last, I'm going to say star result. Now what is result? Result is obviously going to have to be a what? A pointer. It's not clear but you can make this a pointer, right? Type whatever you want. So the result is being assigned OP, which is the unary operator of the first element. So we're going to use, so it looks like OP looks like it's a function call, doesn't it? OP looks like a function call. It looks like a function call of the dereferenced first element. And then I'm going to say plus plus result, and I'm going to say plus plus first. So that's going to move first forward, and the loop might end, or it might have another iteration. If it has another iteration, we're going to get another result. We're going to use this function here, OP, of the second element, which is because after the plus plus, we are assuming we're at the second element, because we didn't terminate. Apply this OP, which is this input operator, this unary operator. Add it to result, or assign it to result, plus plus result, etc., etc., etc. So I want to show you how a simpler functor is going to work. So this is going to be a functor class. So the class is going to be called addX. The class is going to be called addX. This is the private section. This is the private label. Notice that inside this we have an X. That's our private property, X, which is an int. So now what I have is, this is the key right here. This is the key right here. Int operator parenthesis int y definition. This is an inline function. What am I coding? What am I coding? What am I coding? What's this? Please don't say int. What's this? Return type. What's this? So we are overloading an operator. What's this? These are parameters to the operator. Notice that before, when we overloaded operators, right? When we overloaded operators, we don't necessarily have to put any parameters into it. We don't necessarily have to put any parameters into it. Well, we can. So basically what we're saying is this overloaded parentheses operator returns an int, takes an int, and what I'm going to do is I'm going to return whatever you gave me plus what? I'm going to give you whatever you gave me plus the value of my property. What's the value of the property? I don't know. Where is the value of the property set? At the constructor. The class constructor said at x, the parameter is x, the property x gets assigned x. By the way, this is the only place where you can say xx, and this means property and this means parameter, because that's the member initializer. Member initializer always knows that on the outside is the property, on the inside is the parameter. Because the parameter is coming in, and this must be already here, so it must be the property. Okay, so if you look at this, notice that I have addX. So addX is a type, right? It's a class. Add42 is what? It's an object. What's 42? Where's 42 going? It's going to here. So as soon as 42 goes in, it gets set to the x value. Okay? Now I have int I equals add 42, 8. So what am I doing here? Is this an object, right? Add 42 is an object, so what am I doing here? I am invoking the parentheses operator, passing in 8. Where's that 8 going? For which variable? Y. In this host object, what's the value of x? 42. So what's 42 plus 8?
50.
Okay, so that's why I get assigned 50. So when I say that a functor has a state, well, you think about it, basically the property is 42. Why is it 42? Because I constructed a 42. So if I say add 42, 8, it's going to be 50. If I say add 42, 1, it's going to say add 42, 8 is going to be 9. Right? The state of the object can be used in computation. So it looks like I'm calling a function because I can run a function, but I can also use state information of my object. So that's why it looks like a function, but it's really an object calling a function looking overloaded parentheses. Therefore, that's why we call it a functor. Assert I equals 0. You know, is that going to be true or false? That's true? Okay. Now, I want you to take a look at the next code. Vector int in, and we're going to assume this vector contains a bunch of values. And we're going to say vector int out. We're going to assume this vector does not have a bunch of values. We're going to pass a functor to the transform. We're going to pass a functor to the transform. This is the method, correct? This is my vector that has a bunch of values. So I'm sending in.begin. What type is this? What type is in.begin? In pointer. Because it has to return an iterator to vector int, so it's going to be an int pointer. What type is in end? In pointer. So I'm passing. So what that means, if I go back to here, then input iterator first, input iterator last are the pointers to the first and last elements, right? Now, what am I passing in next? The next thing I'm passing in is I'm saying in begin, in end, I'm saying out begin. So I'm passing in the pointer to this vector. Where's this pointer pointing to? At the beginning of the vector. How big is this vector?
0.
No. That's a good guess, but it's not. And the reason it's not is because STL knows that if you create something by default, it's going to give you some space for it to put stuff in there. How much? I forget. But if you keep putting things in there, it will just keep growing the vector. The vector will expand as it needs to expand. So you don't have to worry. Now, of course, it'd be better to create it. If you know you're going to need 10,000, probably a better idea to keep 10,000. Just say 10,000. So it doesn't have to do too much work. So beginning pointer of the iterator, end pointer for the iterator, the beginning of the storage, and then we have add 1x. This is the crazy one. This is the crazy one right here. What is add x? Say it. Very good. Did you guys hear that? That's a good answer. That is a constructor. So I'm constructing an addX object with a 1 in the constructor, which means this addX is going to store 1 in its X private property. Get it? Okay. So now we kind of know what's going on. Let's go back to see what the heck is going on in this code. So now you understand a little bit better. While first is not equal to last, result, what's result? That's dereferencing the target location of the beginning of the output vector. Gets the value of OP star first. If you're looking at this, doesn't this look like a function call? Of course it does. But it's not, is it? What type is OP? What's unary operator? What is that type? What type is unary operator? Say it. It's an addX. Yes. Okay, so unary operator is an ADX, and OP is an ADX instance with a 1 in its constructor. So what's going to happen, I'm going to say OP star first. Star first will dereference the first element, put it into the overloaded method. What is that going to return? It's going to add 1 to the first and assign it into the target of the output vector. Good. And this is going to say plus result. So it's going to move, it's going to iterate to the next location of the result vector, and it's going to go next one to the input vector. And it'll continue doing that. So what it's going to do, it's going to store, what's going on here? It's going to store into this output vector a copy of all of the elements here, adding 1, using a functor. So when you see a functor like this one, it's hard to see whether it's actually a functor or a function. That's why they call it a functor, because it sounds like a function. It behaves like a function, but it's not. Okay, well that was a lot of fun. Okay, let's look at some nice fun code. Not that all the code that we look at is not fun, but let's look at some nice fun code. So you can see some actual code here. So I have output stream, IO stream, I have vector, algorithm, and functional implemented here, or imported here, imported or included. Okay, so the first thing I do is I create an array of int values. Then I say int d equals size of a over size of int. What does that do? That gives me the number of elements. Good. And so then I'm going to say vector int. So I'm creating a vector of type int from this vector header. V a comma a plus d. So it's going to give me what's d? So I'm what is a? A is it's the address of A, so it's a pointer to the 5, if you will. And A plus D is what? That's the pointer to the end of 66. Okay, so I'm constructing a vector with giving it 2 pointers, and those pointers are going to be assumed to be the begin and the end of that collection, each of them moving through integer values. Okay, so now I'm going to say sort. Sort is an algorithm coming from here. Sort v.begin. Remember, when v goes in, the compiler knows that v is a vector. Really v here. V is a vector of int, therefore it knows it's an int pointer to int pointer. It's sorting ints that start at this address and end at that address. And so it's able to easily do a sorting algorithm on this. Then we're going to say for vector int iterator, itr equals vbegin. You understand what I did here? So I basically took an iterator for this vector, I call it itr, and I initialize it to the vector beginning. Itr not equal to v.end, and my additions are going to be here plus itr. Cout slash itr. So this is just going to print the elements of the vector, right? With a space in between. So tick, 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 tick. Now, what I'm going to do is I'm going to instantiate a functor. Greater is a functor in the functional STL. Greater is a functor. So basically I have a greater functor fn. So this functor already knows what to do. But now this functor knows it's going to be comparing ints. So the greater is not only a functor, but it's a template functor, because it's going to return greater for ints. So now we're going to do sort. So it's the same method as before. vBegin, vEnd, but now I'm actually passing into it a functor. And the functor knows how to compare whether one is greater than the other. So this is going to sort in a particular way. Another way to invoke the same notice that this is going to be, so we're using the standard std greater functor. Now, alternative call is sort v begin, v end, greater int. Greater is a class. This is a template type, and so here is a default constructor. So we're constructing a greater int comparator functor. Okay, rather than here, we're actually constructing it and passing it in the object. Here, we're constructing it on the fly. They both work the same way. All right. Let's look at the map associative container. So maps are like hash tables. They are like key value pairs. For example, let's say the key is Aladdin, and the value is his IQ, which is 175. Okay, James is the key IQ 187, even smarter. I don't want to embarrass anybody who has an IQ below 187. Okay, and so maps work just this way. So let's take a look at how you could do it. So notice what I'm doing here. I have a couple of things that I have here that I'd like you to notice. So IOStream is very, very simple. We use it all the time. I have another header called string stream. What a string stream is it allows you to stream from strings. And so what you can do is if you read a string and you put that string into a string stream constructor, then you can use that string like it was a file. And you can C in from the C string, for example, or S in from the C string, whatever you want to do. It has all the operators. Just like an IO stream, string stream has the same thing. So F stream, you know what it is, file stream. And then here we have string, class, object, and then map. Map is an STL container. Okay, let's take a look at this because it's a very exciting program. Very simple, very exciting. Okay, so let's see what happens here. So the first thing I'm going to do is I'm going to create a map object called M. You can see that map is an STL, right? Container. And how many types does map take? It takes 2. So in this case, the key is going to be string, and the value is going to be int. The key is going to be string, and the value is going to be int. And the name is M. So this constructs a map. Now I'm going to go and create an IF stream in to a file called data in, open it for input. Then I'm going to create a string object. Then I'm going to say while in into S. What does it mean what does it mean while I into S? I in into S. While I in into S is true means that we were able to successfully read a string. And of course, you understand how this works, right? How is this working that I can get a true false out of this operator? Because you know the bracket here doesn't return a true false. How do we get the true false? It's a Boolean casting operator. And you know how it probably works. Basically, after this operation happens, there's a flag that's set to good or bad, whether there was a good or bad I.O. And if it's, where is it over here? If it's bad, then this will return false because you're casting this. By the way, what type is in? IF stream. But what type are we actually getting inside the parentheses as a final return type? A Boolean, because of the Boolean casting operator. If you didn't have the Boolean casting operator, it would be a compiler error. Okay, so while I am successfully reading into S, now look very carefully. Map sub S, what's S? It's a string. Map sub S plus plus. Okay, map, think of map as basically a big array, if you want. Has keys on the left side, has values on the right side. So that means that map sub S, or M sub S, is indexing into that array at index S. Like you say, what the heck is that index S? It's a string. So what? You don't worry about it. You don't have to write the code. It basically finds a number for that. And it finds that location and it increases the value at that location by 1. How long is this going to happen?
Until it gets in a file or error.
Until it gets into the file. So can somebody explain to me what they expect to see in the vector m sub s? Or in the vector, in the map of m? What is the state of m?
Series of strings organized by key.
So the map will be a set of strings, and next to the strings,
Their key value. For their index.
next question. How many entries are going to be in the map?
How many strings is there? There's many.
You're thinking, how many entries in the map?
Number of string, element in string.
Not a perfect answer.
Does it automatically split it at spaces?
That's what this does. That's what this does right here.
Okay. So then it would be a series of strings divided, or substrings divided at the spaces.
Well, suppose the file had 100 strings. Then how many elements are in a map?
100.
No. No. That's a good guess. The number of strings in the map. Notice that as I put in S could be the word hello, then a different word, but then it could be another hello. So M sub hello, the second time, goes to the same map, key. So the better answer,
Oh. The number of uniques.
so the better answer is the number of entries in the map will be the number of unique strings. Okay, let's look at the finish here. So next thing I'm going to do is I'm going to create a map string int colon iterator. So I'm creating an iterator, right? An iterator to maps keyed on strings with values of int, which is exactly what we need. And then I'm going to say it equals m.begin. So I give the iterator the beginning of the map, and I say while it not equal to m. Do you see how same it is every single time? It looks the same, right? See out it pointer first. It's a little different. Before we did star it. Now we're saying it pointer first. Okay, tab it pointer second, end line. Can somebody tell me what the heck this is doing? What is it printing? So the iterator gets the beginning of the map. It's not into the end of the map, so we print the iterator pointer first, pointer second.
String key.
So it has a key. So the first is the key, the second is the value. So therefore, tell me what type is it. I know it's a map string it iterator. I get that. Give me a description. What the heck is it? It's a pointer to what?
String.
No.
Well, the first one is an int pointer.
It's a pointer to a what?
Pointer to the map.
No, not a map. Not a map, but a map.
Error, key,
No. A map.
Template.
The entire map entry key value, which must be an instance of what? Of a class. Of a class. You see, before our vectors had tick, 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 tick values. So the iterator just be a pointer to the value. So it's a rational star rational. If it's an int, star int. But here, the map has key values. So therefore, I can't have a pointer to a key value because it's two different things. So what happens is when they make a map in STL, they create a class that contains the key and the value. That's a class. So therefore, when you get an iterator to this type of a map, it's a pointer to that object that has the two pieces. And those two pieces are properties. So the first ends up being the key, and the second one ends up being the value. Here's what it looks like when you run the program. So this is the input file, data in, okay? And here's the file. So hello there, this is a nice way to write a program. Okay, so you see what's going on here? This is the output. Do you see how that works? What did we just do? We counted the occurrence of every unique word. That's all we did. Kind of cool, right? And that's how we did it. By the way, I didn't use any string streams. Yes?
So, does the map initialize all the values to 0? Because you didn't. You seem like you're just incrementing, right? Incrementing what?
Okay, so you're saying here?
Yeah.
Oh, I see what you're saying. Yes. Yes, zeros and nulls and zeros of any type. Right. So it has, so the map, what's another, well, this, I mean, people call it a map. A lot of people use the word map. But what's the old word that still exists? Hash table. It's a hash table, that's what it is. So when you make a map, it immediately, now how big is this map? Notice that when I'm constructing this map, I'm not giving any parameters. I could say 1 million, I could say 100,000, I could say 10. So my size of the map is going to be default. If I start doing things and the whole thing gets filled up, it's going to just double its size and it's going to rehash everything and continue going. So it's going to be time consuming to do that. But the nice thing about the STL containers is that they grow by themselves. So you don't have to worry about having allocated enough memory. If you need more memory, just keep adding stuff in there, they're going to grow. Whether they're vectors or decks or whatever, or maps, anything like that. Okay, the last thing I want to cover real quick is container adapters. So container adapters allow you to use a particular STL as a particular data structure. This is very easy stuff. So stack methods include push, pop, empty, top, and size. Everybody's familiar with that, right? What's pop? I'm just kidding. Queue methods include front, back, push back, pop front. I don't know. I guess these are the methods they like to use. So let's take a look very carefully at this. So I'm going to create a stack of type int, and I'm going to create a queue of string. So see how easy it is? It's very nice, right? Very, very nice. Then I have a stack, and the stack is going to be an int and the vector int s2. And then I have a stack string, and then I'll have a list. Again, this is the STL list for string s3. So I have basically 1, 2, 3, 4 containers. I'm not going to use them all. I'm going to stick with this one s3. So s3 push hello. So what is string? What do you think string is? These are container adapters. Anybody know what string might be? What S3 is a stack, right? So what is string referring to when I'm pushing hello? Element type. It's the element type. So S3 push hello, that means that hello is the element type. What is the list string?
The starting value.
That's the container adapter. And that basically says, I want you to implement a stack of strings, and I want you to organize it by using a linked list of strings. Once you do that, you just say plus plus, blah, blah, blah. You do the same thing as you did before. Okay? So, notice here, I say I'm making a stack of ints, and I want you to organize it as a vector event. What's the difference between a vector and a list, linked list? Vectors are implemented with indexing, buffers, and lists are implemented with pointers. But actually, it doesn't matter to you. Okay? And this is implemented with pointers. But look at this. Push, 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 while not S3 empty, C out, S top, S3 pop. Get the top, print the top, pop it. Boom, 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 boom. It doesn't matter how these point. So it's going through a bunch of pointers, but you never see it. Yes? I know we're running late. Is that what you want to say? Okay, okay. All right. So one last thing here. So here we have, we can create a priority queue, which is going to be storing strings. Vector string is going to be the implementation, and then we're supplying a comparator here for priority queue, which is greater, and that allows the priority queue to put greater values ahead of lesser values. So, priority queue, element, storage, type, and then a comparison function. Okay, I'm going to let you guys go, because it's late.